Well, we're just about there. Welcome back, everyone. Okay, it looks like we can start officially. Welcome back, folks. Last section was probably one of the more exciting sections, I would say, for the entire textbook. I think it's pretty fun thinking differently in terms of logical connectives, truth tables, all that kind of stuff. It feels like a totally different kind of mathematics for me personally, the first time I saw this stuff. And what we're doing in section 3.3 is nothing any too different. It says some extensions, but if I were to title that, I would call it a lot of extensions. We're going to be using the logical connectives, truth tables as a major computational tool to look into a lot of additional topics in propositional logic. Then when we go to the next section, 3.4, next Tuesday, we're going to be moving into predicates, which are propositions whose truth depends on some external variable. So we're going to be extending on that even further, getting into quantifiers, double quantifiers, all that fun stuff in logic. But any questions at the moment, folks, to start us out? Okay, and George asked during the 3.2 section a really great question about logical gates. The NAND operator, the exclusive OR operator, I took a look into the book because I honestly didn't know a good answer to that one. And this is briefly covered in the textbook in section 4.4. Some examples of proof is what our author titles the section. This one's not actually in the syllabus because I felt like it goes really, really heavily off into the deep end of proofs with some pretty technical ideas, slightly out of scope for the actual textbook. But if you're curious with the NAND operator, the NOR operator, we're covering this one, the exclusive OR operator. There's some really nice discussions in that section. Our author is going to use essentially all of the tools of the trade that we're picking up with the logical connectives, the additional topics, the predicates, the quantifiers, to go into new topics on logic with the idea of computer science as the main application to do some hard proofs of some really interesting concepts. So again, it goes a little bit beyond the course, but if you're curious about that, that's some pretty awesome additional reading. Other questions or comments at the moment, folks? Okay, thanks again for asking about that, George. And what we're doing today, again, is just extending on all this stuff. Probably what you would want to have next to you, say a printout or just one big sheet as just one collection, is the truth tables. We're going to be calling these up as a major and massive tool as we get through each problem, just to make sure we know exactly how the biconditional goes, to make sure we know exactly how the implication goes, and to not get mixed up in anything like the negation, the and, the or the exclusive or connectives as we go through the next bit of material. So this is a good thing to have ready to go. And once we start practicing these a lot, it's probably one of those things that you're going to have down pat. So here's how section 3.3 starts. First, it's just kind of a review of information we need, another definition of Boolean because of the connection with the proposition. And the new material is right here, starting in 3.12. We'll say a proposition is satisfiable if it's true under at least one truth assignment. So that makes it a satisfiable proposition. A proposition will be then unsatisfiable if it's not satisfiable. And that's kind of an awesome way to say that. That is 100% logically complete. They're just negating this statement here. But one concept we're going to get into when we get into our quantifiers is we say not satisfiable, we're negating satisfiability, which means we're negating at least one truth assignment. That would mean it's true under no truth assignment whatsoever. It's not a bad idea to just pen that in as a reminder. Unsatisfiable means false for all truth assignments. And just a reminder, what do we mean by truth assignments? We mean these kinds of things when we're looking into the truth tables. The truth assignments were for P are T and F for true and false. So the truth assignments for the negation of P is false, and true. So that's what we mean by unsatisfiable. And the fancy word from logic next is tautology. We'll say a proposition is a tautology if it's true under every single truth assignment. So just always true is a great way to think of tautologies, which means a tautology is just a special kind of satisfiable proposition where it was true with at least one truth assignment. Well, any questions so far, folks, with these three big new definitions?
Yes. So on the previous exam, I did not anticipate so many definitions being in there, which I was greatly appreciative of. Can we
Yeah,
count on these being on the next exam? It might be a bit early to be asking this question.
it's not early at all. I'm glad you asked that. And yeah, you can absolutely count on that. For as far as the exam goes, I'll always have this formula sheet. And if we take a preview, let me go to, let's say, elearn.isu.edu. Here's the preview of the formula sheet we're going to get on the next exam. I don't have it on my thumb drive, so I'm just going back to the good old days of Moodle. Actually, I'm starting to like Canvas a little bit more now that I've actually used it for over one semester. And the preview for what I'll have for upcoming exam two will be, let's see here, there it is. Not exactly this one. I'll let you know exactly what it is once we get there, but this will be about it. I'll have a definition for all of these interesting things like, hey, satisfiable, unsatisfiable, tautology is going to be in there, converse, contrapositive, inverse, and so on. The only thing that's not on here, which we have to now really internalize, is you would have to know the truth tables for each one of these propositions. These would tell you what they look like. You can go from the definition of P and Q. It says it's true when both of propositions P and Q are true, and then construct it right away. So this would be the stuff that we'd have to be able to be ready to construct or have memorized for the exam. And pretty much this kind of sheet right here is what's provided. All of the detailed definitions for the logical connectives. Other questions with that so far? Okay, yeah, and thanks for asking about that again. Once we get about here in the Canvas page, let's see, right around week 7, before we get into week 8, I'll have the definite coverage on exam 2. And the first file I want to create is the handout that's going to be on the last page of the exam, just like on exam 1. Well, here's our big 3 new definitions: satisfiable, unsatisfiable, tautology. And this is a screen grab right out of our textbook. Here are some interesting tautologies. Some of them are mysterious, like these are just interesting little curiosities that we could prove our tautologies. It's hard to say what kind of scenario they might actually enter in. These are more things that might seem just kind of obvious in a certain sense, like, say, for example, double negation. We're saying P if and only if the negation of the negation of P, or not P, that should always be true. We expect a cancellation with double negation. But, we're going to prove that just to show how to demonstrate something really is a tautology. Other ones have nice names like modus ponens, modus tollens. For example, this one says, if you take P implies Q and P, then Q must be true. So this is another nice tautology, and a whole bunch of interesting ones down the line as well. So we're going to start off proving that this one's a tautology and then build from there and wrap back into the definition of satisfiable, unsatisfiable versus a tautology. Any questions or comments so far? Okay, let's give this a start on part A then. It says show it's a tautology, and we'll use truth tables. This will be the major requirement for the homework in demonstrating our work. Essentially, that is the work right there once we list out the truth table. So begin by writing out P. This one's kind of nice. If there's one proposition, I just need 2 additional values down below. So 2 rows below P. It can have a truth assignment of true or false, nothing in between. And we're looking at not P. Well, there's a kind of order of operations in there. When you see not P, it's assuming we mean really not of not P. So much like F double prime means F prime prime, same idea with the double negation operator when we just stack the connective in that way. So really the first thing I'd want to do is work inwards, start with not P. This is really now just the truth table from section 3.2. The negation of P will flip the truth assignment, so we'll get false and then true. Then the negation of P, the negation of not P, I'll just write it in its more simplified version without parentheses, flips the truth assignment, so we'll get true, false, and we're not quite done. So far, all I really have is P right here and not P. But the thing we're showing as a truth assignment is really the biconditional statement. So we need to put this down on the truth table next. So this is our final row, or rather, that's a column, I would suppose. P, if and only if, not P. It sounds weird just to say that. Here, we need to really know what do we mean by the biconditional. Well, the biconditional will always output true if the truth assignments on one side and the other side are identical. So thinking in terms of that truth table, here it is on the very bottom. Notice it only ever gives you a false when the truth assignments come out differently. So this is kind of tricky. If we're connecting P with not P and you see falses, there's almost a temptation to put false down, but that's true. The biconditional outputs true only when truth assignments are identical. So we do get true on this one. We're connecting false with false, and true with true we're connecting, getting true as well. So now we can wind back. What was a tautology? We say we have a tautology if it is true under every single possible truth assignment. P only was the only proposition, so true and false were all possible truth assignments. And we got true as an output on every single one of them. So that means our work is done. We can conclude P if and only if not P is a tautology. And that's our first one. It's an honest proof in logic showing that this is a tautology, and it's kind of fun in a way. It's just relying on the truth table, which relied on other truth tables. So these are starting to stack together in a certain sense. Any questions at all, folks, computing through this one? Okay, it's kind of a fun way to compute again. Totally different from anything you might have done in an algebra class, calculus class, differential equations class. This is like its own new way of thinking all to it on itself, but it connects. So whenever you're looking in theorems in other math classes, you might have seen theorems along the lines of if P then Q. You might have seen theorems that said following statements are logically equivalent. We're really thinking directly in those terms. And it's kind of weird to have to face those big technical theorems without absorbing this material here. So this is some pretty great work in both mathematics and computer science. Didn't mean to do that. Let me put that back. Let's do this again with part B. Should get a little bit of space on this one. And let's hide part C for the moment. So this one says P and Q implies P is a tautology. Well, let's check that out. If we want to write this one down, we have two propositions to work through. But because there's two propositions, we need 2 to the power of 2, 4 rows altogether below our heading for both P and Q. So sometimes our tables are going to get kind of mean and messy and large. I could always use the table tool in Microsoft Word, but I think most people are possibly doing this by hand. So out of the sense of solidarity, I'll do all of these by hand as well. So my table doesn't have to be this big, just 4 rows, but let's go with big for visualizing this well. First, my truth assignment standard for both P and Q are true, true, false, false for P. Then true, false for Q. Now what we want to do is just break this up. Let's work on the left side first, P and Q. So this is the and conditional. This means this will only ever be true when both P and Q are true at the same time. That happens exactly once on this table. And now everything else is false. So that takes care of that. This is P and Q implies P, and I already have P on the table. But when you look into this implication, the direction is important, and it's easy to kind of get things backwards if I'm thinking P implies P and Q. That's a whole different statement. So just for the sake of being careful, it's not a bad idea to just put it down again. Here's P again. I'm going to put down same truth assignments, true, true, false, false. And the reason is I'm going left to right when I'm thinking through the implication arrow here. So here's the overall statement. P and Q implies P. One question you might have already is, how do we know if this is not Q implies P and Q implies P? What if we thought about it this way? We're actually doing a whole different problem. So there's something implicit here, right? There was a type of order of operations. When I saw this on paper, I immediately assumed we're doing that first, and then the implication. And I try to usually put in parentheses, especially if it's going to be a lot of stuff going all at once, just for the sake of clarity. But down below here, there is an order of operations, and implication's kind of low on the list. Negation binds the tightest. The and operator, kind of like multiplication, is next. The or operator, kind of like addition by analogy, is next. And implication by conditional are on the last ones. So that's how I knew it was really this. That's a good table to take a look into. I think it's actually printed in 3.2, but it becomes pretty relevant in this section, 3.3. And again, when I write exams, if it becomes more convoluted than this, I'll start inserting parentheses just to make it as clear as possible. That's usually the best practice. But here's what we're really looking into. And this one, again, is tricky. We're going left to right. And this one is false in only one particular row. Here's the experience. If you're saying doing this in an exam setting, you might want to just jot this down somewhere, maybe on a piece of scratch paper, go to the implication, and the implication is telling us we get false in one exact spot. So if we find that false, we'll know everything else flips to true on this table. False occurs when we have P implies Q going from a true to a false. And this is playing the whole role of the P, this is playing the whole role of the Q, and we went from never happened, did it? It's always true to true, vacuously true, vacuously true, vacuously true. There's no false whatsoever on this table. That's good because we're trying to prove it's a tautology, so it tells us, hey, we're on the right track. True, 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 and true. But just because a problem says it's a tautology doesn't mean we should just put that down because we're expecting it. If something did flip to false because we had the wrong assignments here, that's a good time to double check and correct a mistake on the prior columns. But all truth assignments here became true, so we can say, therefore, P and Q implies P is a tautology. And that's the second one down. It's kind of a fun problem because, again, we're very strongly directly reviewing every single logical connective pretty much in these notes. Any questions at all, folks, with this second table down? Okay, so I had 4 rows going down below the heading row on this table because there was 2 propositions. And this is the nasty one. There'll be some of these in the homework, not tons of these, but now there are 3 propositions. That means we need 8 rows. There's 4 propositions, there's 16 rows, and so on. Even though this is not the worst thing in the world to do computationally, you can imagine if there is 5 different propositions, 2 to the power 5 is 32, you need 32 rows. That just starts to become some pretty serious tedium at that point. So as far as an exam goes, and I think with the homework as well, I'm going to max this out at 3 propositions. We get the point at that stage. four propositions just feels like extremely tedious, busy work. But this is a good one that could come up on exam and homework. I'm going to need a lot of space on this, so we'll scroll in a moment. We have P, Q, and R. So let's start off with a really long table here.
So I got a quick question.
Yeah, go ahead.
This is more of an expansion on the larger sets. Uh, because those get so complex, human error is very likely to enter. Are there programs that can do that kind of thing, like MATLAB?
Oh yeah, absolutely. So yeah, this all the stuff could be just directly coded in, and you could just input your propositions, various truth assignments, or just have it compute the entire table. So yeah, there are systems to do that kind of work for us. Because yeah, this becomes just not feasibly possible if we have some really complicated statements, maybe who knows, 70 propositions, but it does become kind of exponential in growth of how complex it could get. Other questions at the moment? Now, that's a good question I want to come back to when we come back on Tuesday. I know these kinds of things exist, but I don't happen to have the name of a particular process or program that can do it. It might be built into something like Mathematica, MATLAB, like you were saying. But I want to come back to that comment. Find programs for truth table computations. I think that's going to be kind of a fun side project as well to take a look into. Other questions so far? Okay, well, let's delve into this one. Whenever you see three propositions and pretty big compound statement like this one right here, parentheses just for extra clarity, definitely it's a good idea to just go slow, methodical. The first thing we want to build out is the first three columns and show all possible truth assignment pairs or triples for P, Q, and R. So this is going to be my best attempt at by hand penmanship on this. It might get kind of wonky at it as we go. So I'm going to need 8 rows now, additionally. Drank a lot of coffee today, but somehow it hasn't taken effect yet, I can tell. I lost count though. They're kind of starting to get unstable. So I've got 1, 2, 3, 4, 5, 6, 7th cell is below. And what the heck, one more row for the 8th cell. Okay, so that's the gigantic table for just 3 propositions. Let's put down P, Q, and R. Penmanship count, so let me know if something looks kind of funny. And all possible combinations, it's not too bad to build out. What I'm going to do is just borrow this structure right here. I'm going to start with just P and Q, just duplicating that. So I'll go true, true, false, false, true, false, true, false. Then for R, I'm just going to put them all to true. True, 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 true. Now I'm going to duplicate these rows right here down below. True, true, false, false, true, false, true, false. And now we finally have every possible combination if I just put out falses on all these cells for R. False, 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 and false. So now they're all there. And just a reminder and duplicate a comment from section 3.2. If you have a different system that just works for you, a different way of putting all these down, you don't have to change. Keep on working that same system. It's going to be easier to do this if you're very consistent each time you do it. And if I see everything there, if you have a different system, I'll have to look really, really carefully, but that'll be all right. I'll check I've got everything there and then check the next columns. Well, that's a start. Now look what we're doing. We're breaking down an implication here, here, and here, as well as an and operator at the same time. So there's lots of different ways we could go at this. let's maybe just start with P implies Q. Let's go left to right on this. So P implies Q to start. So again, the thought with P implies Q is it's false in two spots because I've duplicated the table for P implies Q. So I'm just looking for two falses. This is a false right here. P is true and Q is false. P implies Q is false. And same right here. We'll get a false on this line. Now that we found all the false possibilities, it's not too hard to fill in the rest. Everything else is either true or vacuously true. So let's put in T for all the remaining cells. So here's P implies Q. Let's put in Q implies R, and maybe the entire compound statement right after. So Q implies R next. Again, going slow is going fast for these kind of problems. You want to be as methodical as possible so we don't just accidentally miss something. So now Q implies R, my eyes are pretty much focused here where it's highlighted yellow. We want to find the two falses. There's no way you get a false when there's a true, but you could get a false, say, here. Q implies R is false on this one. Let's just pull up the table because we went from a true assignment to a false assignment there. So much like this one for P and Q. So let me make sure I get the right cell. True to false here gives me false on this line. And true to false is duplicated down here, so false in that cell as well. Now let me know if I ever miss anything. This is a lot of chances to make just one simple mistake with all these cells. So true everywhere else on the implication. Okay, so that's down. Now we're doing this big statement right here. P implies Q and Q implies R. Really, the major thing we're focusing on is just the AND operator. So this one's not too bad. Let me just first put it down. P implies Q and Q implies R. So now we're focusing on these two columns particularly, but just thinking in terms of the AND operation. There's a whole ton of symbols here, but again, just focus on the one thing that's new, that logical connective. AND is going to give us mostly falses. This will only ever be true when both things on the left and the right output a true. So this time for the AND operator, hunch for the trues, and it can make this a little bit faster. It's true on this cell because we have double truth assignments, false, true here, true here, then false, 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 true one last time at the very bottom. Okay, so let's double check with the AND operator. We should be getting false on this one, false on this one, then false, and finally false. So I got 3 true outputs altogether, excuse me, 4 of them altogether on this one. Does that look about right to everyone so far?
Yes. I have another question about formatting.
Yeah,
Or two. So, uh, we're getting a lot of these symbols, uh, really complex, really fast. So could we do an assignment like uh G equals P implies Q, and then another one, and then just do G and uh like H for Q implies R,
yeah, absolutely. I like that. So
and
yeah,
then
simplifying this down so we're not looking at all of this basically noise, right? We just want to focus on the AND operator. So if you rethought of this as a G and, let's go with, that looks like let me fix that. G and, I like the suggestion, H implies maybe say R, this being the R over here. This is really the whole punchline to it, right? We've simplified down to just these compound statements. This is the G, this is the H, implies R. Yeah, I'd say that'd be an awesome way to go. And that's helpful on the eyes because again, it's easy to get lost in the weeds when you're looking at this big statement. So if all you said is G, I'd say that's a fantastic way to format. In fact, let's borrow this. I'm going to pick that up and rewrite this as a R on the next one. And then I'll use this for my final column. I think that's a great suggestion. Other questions so far?
Yeah, one more.
Well,
Um,
that's two, right? Yeah.
yeah. So with all this, the T's and F's get really clunky really fast. So I'm wondering
Mhm.
if we could put down that T's are true, but falses are blank or something like that. Or if you want to be completely um, correct.
I would say if you went with that route, just make a note on your homework paper. Blanks are going to be my outputs for a false. T is going to be my true. So if you just make one quick note on the paper so I know exactly what your system is, that'd be fantastic. Any system that makes sense, I'm all for. Some people would rather go zeros and ones, for example, where maybe zero implies the false, one implies the true, and then use your system. So my ones are just going to apply a true, blanks are going to apply a zero for false. Any kind of system like that, as long as you tell the reader, me, exactly what it is, that'd just be a really fast note to put down. That'd be terrific. And yeah, that would save us from kind of getting lost and mesmerized by all the symbols that we're putting down on a big table like this one. But does that make sense for that question there?
Yeah, thank you.
You bet. Those are great suggestions. Thanks for asking about those. Any other questions or comments so far? Oh, let me fix my symbolism here. This is shorthanded to G and H, if you prefer the shorthands. And let's keep on going with the shorthands. That's a great suggestion for this. We're going to put down R next. You notice we never have done that one. I want to do the G and H first, this big compound statement, because the last thing we're taking a look into is an implication one more time. So I want to have the if P right here and the big Q right here to analyze that implication, not get things backwards or any wires crossed. So here's next R, defined as P implies R specifically. With P implies R, we're looking into this entire column. Let me just highlight the whole thing this time. And this entire column. Now, with this implication going that way, I'm going to look for the vacuous, or excuse me, the falses first. We'll get a false whenever we go from true to false and P implies R. So we're okay through here. And looks like these two in a row are the only falses we're going to pick up. So we went from true to false here. So false on this cell. True to false here. So again, false on this cell. It's a good idea to double check, but true to true is always true. So I have a true, true. We start with false. These are vacuously true. So we'll get a true, true, true to false. We put down these, no matter what happened on the right, output a true as well. So true and true. So again, that's just massive amounts of applications of the implication right here getting through this one. Does that look about right to folks on this brand new column? Okay, one last one to get through. So one big column, and let's shorthand it again. This is a great suggestion. Let's go G and H. The only thing really new this time is we're looking into the implication implies R. So let me reset the focus. This time we're looking into these columns here, but we're analyzing it through an implication statement once again. And we're on the right track if we only get trues because we're expecting a tautology on this one. So true to true is great. We'll get a true. Falses means we don't have to look too far. We get a true automatically. Two truths in a row going from true to true. False, false, false. Those are automatically true, true, and true. And we got there. True to true will give us true on the implication again. And our work is complete. So we can say, therefore, let's shorthand this statement. It, referring to the original big compound statement, it is a tautology. Definitely a lot of work though, right? So you can imagine this would be probably just not really very feasible, even in the classroom setting, to try to fit four propositions, 16 rows. That's just, I'd have to zoom way out. We're going to have to use a lot of different kinds of shorthands, maybe an actual table structure in Microsoft Word to make that work. But this is going to be as big as our tables would get in either a homework or an exam situation. Probably in an exam, I would say maybe one of these at most because of the tedium involved. Any last questions at all, though, folks? Proving a tautology for this one. Okay, so we mostly just focused on tautology so far. The next example is just building a little bit more on that. Also mentioning the standard logical hierarchy that is effectively the order of operations for these logical connectives. I mentioned here for best practices, it's not a bad idea to just put parentheses around things just for extra clarity. And I'll try to always do that as well whenever we're writing down, say, a question on an exam. I wouldn't want to strip off as many parentheses as possible just to say, oh, see the hierarchy chart. Clarity is a good thing as well in writing, so I'll try to always include these kind of parentheses. I won't try to overload it with parentheses, so you could have put in this extra one right here to really imply the implication goes this way. But for what we're going to do in example 2 is just a couple more practice problems, this time with all three definitions on the table as at once. Recall satisfiable just is going to mean there is the proposition or the statement is going to be true under at least one some truth assignment. Unsatisfiable, kind of the opposite of a tautology, is going to mean always false. And a tautology will mean always true under any truth assignment. So here's another random one to give a try, P and Q or P and not Q. We'll look at that one down below later. So to practice this one, I think this one's kind of a break based on what we did on the last problem. Only difference is it maybe has, well, about the same amount of columns, just less rows to worry about. So this should do well for the table structure. We'll go PQ, so true, true, false, false, then true, false, true, false. And let's see what we have here. The major thing that we're going to check on the end statement is going to be the OR operator. Here we have P and Q, so let's maybe start with this side, P and Q. As a logical connective, P and Q is a fast one because it's false in just about every single situation, true in exactly one spot. Well, P and Q must be true, or P and Q to be true. That sounds redundant when you say it that way. False everywhere else. Next, we can do P and not Q, and that's not a bad one to do just as one column. You'd have to do not Q in your head, and that would be allowed if you're okay with that, say on a homework or an exam situation. But I guarantee you, if I try to do P and not Q and I'm not super careful, I'm probably going to mess this up. So this is for the sake of accuracy. Doesn't hurt to put not Q down on paper first. So I don't have to worry about flipping too many things at once as I go through this table. So this will go false, true, false, true for the not operator. Now at that stage, I'm going to be like 10 times more accurate when I look at P and not Q. So for our P and not Q, we're going to be looking at this column, this column. It's another and statement. So let's see, we're going to get true here. We have true to true on this assignment. And false, false automatically gives us false outputs. This goes true to false, so we have false on this one as well. So that's my claim for P and not Q. False, true, false, false. Does that look about all right to folks so far? Okay, and then thinking in terms of just putting down one quick variable to stand for the compound statement, we could think of this as P or, excuse me, G, or let's go with H. So the whole original statement, G or H, means we're now looking into, try target that better, just this column here for G and this column here for our H. This time we're doing the OR operator, so we're, in this real sense, flipping things quite around. With the AND operator, we only had one true statement. But now for the OR operator, the thing I would be hunting for first, just to make it easier on the eyes, is find out where it's false first, because everything else is going to just default to true. False means both things under consideration have false assignments. So let's say here we're going to get a true, true, but that's false, going false to false. And we have false and false here for both of those statements. So false also on this output. So true and just one spot gets us true overall. False here, but true here gives us a true. And our work is about done. We just have to decide, where does this fit in now? What would you all call this statement? Is this satisfiable, unsatisfiable, or is it a tautology? Yeah, absolutely. The moment we got to just one true statement there, a true and the false, it actually doesn't even matter what this was. We can answer the question right to this cell in the table because we have trues, one false, can't be a tautology. When we got a true, can't be unsatisfiable. This is one way to satisfy it. One false, though, tells us that's the overall conclusion. This is satisfiable. But I think it is best practice to just complete the table. So I'll put that back. We'll say here, therefore, it is satisfiable. And our conclusion is done on this one. So this time, not a tautology. We'll look into one more before we change gears into a new topic. But any questions so far, folks, before we try out this new one? Okay, big idea with this one is there are two AND operators this time working. We have things that have parentheses around just for the order of the logical connectives on this. And it seems like it's kind of rude in a way because this is a truth table for just one AND operation. You know, if there was P and Q and R, the same kind of idea implies you're only going to get a true across those two AND operations if you have a true assignment here, here, and here simultaneously. One false assignment on any one of those three spots will give you false overall. So even though it's an extension of this, it's following the same idea, the same logic. And thinking in terms of chunks, let me call this one G. Let's use a variable for this, H. And I guess we could just leave that one in P. That one's just fine as it is. This table is not too bad either, but looks like it's going to have lots of columns, so let's be careful on its organization. Okay, that should do the job going that way. So now we have P and Q. Let's state these as true, true, false, false, true, false, true, false. And now we're ready to go. I'll start with this statement here, G. P implies Q. And this one's not too bad. The implication gives us false right on this row, true elsewhere. So with that one done, let's see. P implies not Q. Again, if you want to kind of just take a shortcut here, you don't have to have not Q on the table, but just be extra, extra careful. I'm going to put not Q on here just again for the sake of carefulness and precision. So if I were doing P and not Q, first I'm going to take care of that. This is going to be false, true, false, true. So flipping the assignments. Now the whole statement. P implies not Q. So now we're going from this P column to this Q column right here. And again, it's not a bad idea to just always refresh. Don't get kind of mixed up on any of the connectives. It's just this implies, oh, hang on. Don't go that way. We're going from here to P implies, no, that was right. Sorry, I just confused myself on that. We're going from P to Q on this one, and we're still using this as the rule set. So I'm going to look for where we might get a false. We have a false on just the very first row, true to false. And looks like everything else is going to evaluate to true on that one. So here's our one false output, going from here to here. False on this cell. This goes from true to true, so true. False to false, so true as well, and true here as well. So that takes care of P implies not Q. And now we're just about done. We can look into the entire compound statement, put it all together. This is effectively now just G and H and P, where this is the column for G, this is the column for H. Using ands as logical connectives means only way we get true is if all three parts, all three propositions, whether it's the single one or the compound one, they have to come out as true as well. So we're analyzing this column, and this column for the far right side P. So the moment you get any falses, the whole thing outputs to false. So we can just put false here and here just by default, because we have a false on P on those two rows on the very bottom. So it doesn't even matter what happens on these columns whatsoever. Now I have a true here, so there's a possibility of a true. But notice there's a false on this one, so whole thing is false the moment one false occurs. So now it goes true, true, but false here as well. So false altogether, and our work is done on this. It's all false altogether. So we can say, therefore, it is unsatisfiable. And our work is done on this one. Well, if you ever saw this statement out in the wild, who knows what statement this might look like as a real world English statement. But if anyone ever says this, now you know that statement can never be true. Logically, it's always got to be a false statement. But you know, here's another interesting related thought as well. If you said negation of P implies Q and P implies not Q and P, we can say this is a tautology, because the negation of this entire big statement would just flip all these back to true. So if something's unsatisfiable, negation is tautology at that point. Well, that's our big rundown on those three new definitions for these notes: satisfiable, unsatisfiable, and tautology. But the major work we're doing is learning how to extend these truth tables we defined before into kind of a computational work here to prove certain kind of results. Any questions or comments so far with what we've done? Okay, next thing we're going to do is look into the implication again. This is one of those statements where there is so much to say about P implies Q. It's kind of amazing in that certain sense. And our extension is going to look like this. We're going to look into topics of converse, contrapositive, inverse. We mean converse to that implication, or contrapositive to P implies Q, or the inverse to P implies Q. At the same time, we're also going to look into the meaning of logical equivalent. Logical equivalence is not the same as a tautology. So that's one thing that can be kind of tricky in a certain sense. The formal definition says two propositions, say phi and psi, will be logically equivalent, and we'll use this stacked equality symbol to mean logical equivalence if they have identical truth tables. So that means there could be falses for phi, falses for psi, but those falses have to occur in the same spots of the truth tables. Same for the truths as well. A tautology means only true for the entire statement phi. But when it comes to logical equivalence, there's a connection. We're saying psi and phi are logically equivalent if they have identical truth tables. But in other words, they are logically equivalent if phi, if and only if psi, is itself a tautology. And the reason we can say that is if we look into the biconditional, way down here, identical truth tables, you combine that with the by implication, this outputs a true whenever we have identical truth assignments. So that's how tautology connects in with this concept. But for the moment, we're just going to focus on logical equivalence itself as being this. The truth assignments for phi and psi are identical, whether they're truths or falses. So we're going back to the ordinary implication, the humble P implies Q, or if P then Q, and this is another way to say it. We want to determine whether the converse, contrapositive, or the inverse is logically equivalent to the original P implies Q. So this one's the superstar here. And these are the new things that we're going to be investigating, looking for logical equivalence. One of them is, and the other aren't, although the converse is an interesting statement, the contrapositive and the inverse, they're all interesting, but only exactly one is logically equivalent. And by the way, does anyone happen to know which one would be logically equivalent?
I'm guessing it would be the converse.
Turns out it's not the converse on this one, which is kind of a big surprise sometimes. It's going to be, it turns out, the contrapositive, kind of a weird statement as well. This one turns out to be the one that's logically equivalent. But the only way to know for sure is we have to compute this. So we're going to bust out another truth table. We're going to put down all of these statements as well with P implies Q and see where exactly they have identical truth tables. So let's get started and see if this really pans out. Looks like a big row this time, or big row this time going this way. Okay, so there's always kind of a mental break as we just get the table ready to go. And what's 1, 2, 3, 4, that should do. Here's P, here's Q to start us out. So true, true, false, false. Okay, now that we have that down, we're comparing P implies Q, so let's start by putting that down, to everything else. P implies Q. And the truth assignment to that one, we've looked in quite a bit. Row 2 gives us the only false, true elsewhere. And now let's just go down the line. Let's do the converse next. Let's label these as we go, that can't hurt. So this is the implication. Next, we're looking into Q implies P. This one is the converse. Let's drop that down. So if we're going Q implies P, this is really kind of tricky for my brain because I'm usually thinking with the implication direction, go left to right. This time we're going right to left. So the conclusion's on the right-hand side, the hypothesis is on the left. So be really careful with this one. So we're going true to true. This one would be true. false, but we're going right to left. This is vacuously true. Doesn't matter what's on the right. So true as well. But true implies false. This is the one false on the table. And false here would give us a true assignment. Again, that kind of hurts my eyes. It makes me almost go cross-eyed because we're going backwards this time. So think this direction, right to left, using this idea here. Does that make sense to folks on the truth assignments for this one? Okay, it looks like we lost logical equivalence on the converse. It's a match on row 1 and on row 4, but it's flipped on row 2 and row 3. It's really close to being logically equivalent, but it doesn't quite get there. For some truth assignments, they are flipped, so we don't have identical truth tables. So let's make it just a conclusion down below. If I can fit that, let me just go here. P implies Q, and Q implies P are not logically equivalent. So let's go off to the next one. Next, we have the contrapositive, and that one's kind of annoying because we have a different order, Q to P, but it's also in a negation, not Q, not P. So let me just put this in just as extra precision getting through this one. Let me flip my truth assignments so I know exactly where I'm going on each one. So not Q, not P. First, flipping assignments for Q. This will go false, true, false, true. Now flip the assignments for P. We have false, false, true, true. And now with that little bit of extra work, I'm going to be way more accurate right here. We're doing the direction, not Q, implies not P. So this one is the contrapositive. Oh, I see that. So for not P, I went false to true. Thanks for spotting that one. That was going to make all sorts of havoc come down on the table next. So this one should have been true as well. Thanks for spotting that. So now for contrapositive, we're ready to go with that correction. The claim is possibly going to work out. I'm claiming P implies Q is logically equivalent to the contrapositive, not Q implies not P. So let's check this out. From a starting position of false, we get vacuously true. From true implies false, we get a false on this one. Then vacuously true as well. True to true is our standard kind of truth on the implication. And there's a lot of stuff on table, so keep in mind we're comparing P implies Q all the way over to contrapositive, not Q implies not P. And if we go row by row by row, especially with the correction that we made, getting the actual true on this one, they absolutely have identical truth assignments. That means P implies Q is the same statement logically as not Q implies not P. Sure, we're just going to say logically equivalent and move on, but this has a major impact on some of the things we're going to be doing later on. We're going to be attempting proofs of certain statements, and some statements in the form P implies Q take an extreme amount of ingenuity, creativity, and computational power to prove, whereas the contrapositive statement is a far easier proof. Because it's logically equivalent to the implication, if you can prove a contrapositive, you have in fact proven the implication statement as well. So this turns into one of the first very major proof techniques. In fact, we'll show how it goes at the very bottom of these notes. Let's state here as just an overall statement. P implies Q, and not Q implies not P are logically equivalent.
So I'm guessing that De Morgan's methods only work on each side of the implication. They don't go across the implication itself.
You mean for De Morgan's laws for, say, negating P implies Q?
Yeah.
Oh yeah, so the negation of P implies Q does work out in a kind of a different way. And I think I have that down the line somewhere in here. Negation of P implies Q turns out to be logically equivalent to P and not Q. Really weird, right? So yeah, De Morgan's laws doesn't work on this one. We'll have a lot to say about this statement because this one is really, really weird. You're just going to
Excuse
have to,
me, Professor.
yeah,
Could you go up real quick for the... Sorry, I just didn't see the P, Q, not P are logically equivalent.
gotcha. No worries. Other questions so far?
Thank you.
Yep, you bet. But yeah, De Morgan's laws don't quite work out for this one. We get some really pretty weird looking object that we're going to take a look into next. And yeah, thanks for asking about getting back to this. I forgot we just barely put it on paper and scrolled away from it. Other questions or comments at the moment? Okay, well, next one is the inverse. It almost looks like a contrapositive, but the only difference between the contrapositive and the inverse is it maintains the same direction. We go not P implies not Q. And I have to be totally honest, I've never heard of the statement inverse as a grouping like this until I read this book. So this one's kind of new to me. I'll have to think about why it needed a name. It's got to be for a good reason. If there's a name for a logical connective like this, there's probably a good reason for that. But this one was new to me. I read it for the first time in our own textbook. Let's take a look at what it'll be. We have the not P, we have the not Q, but the direction we have to be super mindful of. We're going backwards this way. So the last one is not P implies not Q. Let me reset the highlighting so our eyes don't get distracted. So we're looking into this column and this column, but we're going this way through the implication. That's too many arrows. Let's just make it go like this. I think this conveys it just fine. Okay, so again, being really careful with this one, because of the directionality, we start from false, we get a true. So true here, true here. Let me skip down to this one because if it's all true, the direction doesn't matter. You get true on that one. But this one, going right to left, goes from a true into a false. This one is the only false statement altogether. So that's our last portion of the table to complete. For all of these, we're comparing whatever we've computed against the original implication P implies Q. And this has true to true, but false to true, true to false, and true to true. Not quite there. But you know what? It wasn't part of the question. Take a look at this one. Not P implies not Q. And the converse, those have the same truth assignments, they're logically equivalent. But that's just because this is the contrapositive of the converse. That's the only reason it came out as logically equivalent. Contrapositive was the action on this one. If you take the contrapositive of this, you start with not P, there it is. You say it implies not Q, and there it is again. So that's the only reason we saw that logical equivalence. But to fill out or to write out the instructions following exactly what they said, we'll just say P implies Q, and not P implies not Q are not logically equivalent. So this is the big one that we'll come back to, particularly in chapter 4. This turns into just a proof technique in its own right. Consider the contrapositive statement, try to prove that if the original implication is just too convoluted and tricky to work with. Well, any last questions at all, folks? Thinking about these three big statements so far? Okay, so far in these notes, the big takeaways are we're looking into satisfiable versus unsatisfiable versus tautology. The next three big things we're looking into are the converse, contrapositive, and inverse of an ordinary implication. we're going to end this notes looking into just more logically equivalent statements, propositions. And there's a whole bunch. I'm not going to necessarily say we're going to prove every single one of them, or you have to memorize every single one of them. I just thought this was a really cool table out of our textbook, so I just stole it and put it in our notes for today. There's lots of great stuff here. Idempotence comes up in a lot of contexts, linear algebra for matrix multiplication, just a lot of different kinds of things. Associativity is pretty interesting. It's saying if you have P or Q and R, you can just reassociate in this kind of way. Commutativity probably makes sense. P or Q is logically equivalent to Q or P. The order of the propositions is irrelevant. We can prove every single one of these just through a nice truth table. The ones that are kind of interesting are distribution properties. And distributes over OR in this kind of way. P and Q or R, you keep this OR right here, and the and distributes through in this kind of way. And this may be one more call out to set theory, because everything you see here is pretty much a set theory property as well. If these were sets, and you said A intersect B union C, thinking of intersection as and, union as or, this is equal as sets. Here we say logically equivalent because they're propositions, not sets. It's equal to A intersect B union A intersect C. So you can distribute an intersection through a union, and same idea over here, you can distribute an and through an or, and vice versa with the ors and ands as well. So that's a pretty cool property. The contrapositive is the big one that we were just looking into. This is a big logically equivalent statement that we come back to quite a bit, and a whole bunch of other stuff like mutual implication. And hey, De Morgan's laws of logic come back. We briefly talked about this when we were at the very end of the 3.2 notes. So yes, these are formal and real logically equivalent statements. Well, let's see how we're doing on time. Show the truth using truth tables that the following logical equivalence holds. I think I'd have to really rush through to get through this one, but this is a pretty interesting statement as well. And I have one comment that I want to give when we complete the truth table, but since we're kind of shy on time, let me put the comment down now. P implies Q is a really interesting statement. The negation is P and not Q. No implication there whatsoever. And it gets even weirder when you do this. Negation of P implies Q. Well, if we group like this, let me just make the penmanship look a little bit better. If we group like this and use this logical equivalence, this whole thing inside the brackets is logically equivalent to P and not Q, but negated. Then, there's an and there, and now you can use De Morgan's law of logic to push that negation through, and flips to an or, and we negate both propositions. So here's the next logical equivalence, not P, or not Q. We know from our very first problem of these notes, that's just Q. You know what we also know from the very first problem of these notes? This one is going to be logically equivalent to P implies Q. So P implies Q as a statement is the same as not P or Q. That is really kind of bizarre altogether. It starts with this one. We'll prove this one using truth tables. This is a consequence, but we could prove this one from scratch also, just using truth tables to see if this really connects over here. So as a process, truth tables are very, very powerful. But we're also noticing the limitation. If I have, say, 12 propositions and some really convoluted statement like something from here, I'm not going to be able to do this by hand in a day. It's probably going to take me quite a few days to make sure everything falls into place. So there's got to be some interesting software about that, and I'll look into that and talk about it when we come back next class. But any last questions or comments, folks, before we end a little bit early today? Okay. We'll come back a little bit more fresh, review logical equivalence, and do a couple interesting ones. This one's more just for the sake of practice when there's three propositions. We'll end these notes looking at how the contrapositive helps with proving a statement like this one, and then move into the new landscape of logic, predicates, which is going to get us into universal and existential quantifiers. But have a great weekend, folks. Have an awesome President's Day. We'll be back to this on Tuesday. Thanks. Have a good one. Thanks. Awesome. Thanks.